2-ish. Alright, well I'm ready, so I'm going to go ahead and start. Alright, so on my reminders, 1, we'll do a group quiz today. 2, you have mastering due tonight, Monday and Wednesday, so as you're looking forward on your calendar. Tonight covers chapter 12, which we did. You finished chapter 12 Wednesday. Monday covers what we're doing today. Then Wednesday covers what we're doing next week. So, and then we have a test coming up soon-ish. So, if you're starting to panic, the chemistry help room is now officially open, and those are the hours they are open. Pretty much every day, noonish till about 4, just depending. Yeah. When, I think it's like February 4th. I think that's right. Yeah. Okay. I'm thinking not February 4th. Alrighty. So last time we looked at predicting rates of reaction rate equations, right, with the fractions and things like that. Theoretical. We are now ready to make some predictions using actual data. So, let's say I have this reaction. I have A that breaks apart and becomes 2 B's. And I collected all this experimental data. At each time, I looked to see how much B was being produced over time. Right? So I would like to know what the rate of this reaction is. And I'm going to look at the rate of, because I collected B data, I'm going to look at the rate of B appearing. And in order to calculate these things, right, this is change in concentration divided by change in time. So we're going to compare 2 data points. All right, these 2 data points. And how would I go about figuring out what is the numerator? What is the change in B? How do I calculate that? Yeah, 3, 2, 6 minus 0 divided by 10. Right, 10 seconds. That's how long the data was. Let's see, 0.326 divided by 10. Yeah, I did it on purpose. There we go. Pretty exciting. I'm learning all the new tricks. Like this document camera has a lot of fun features I haven't quite used yet. So I'm working on it. Alright, so that's change in concentration divided by change in time, right? So that's 1 new data point. I could look at, right, this change and do 0.572 minus 0.326 divided by another 10-second difference. So how many more times could I do that given the data? 2, right? I could look at this change and I could look at this change. Alright, and we would solve them the same way. Where I would look at the change in concentration divided by the change in time. I'll go ahead and say that this one is 0.0178 and this. Alright, so as my experiment has gone forward, my rate at the very beginning was 0.0326. Then 20 seconds in, it was 0.0246. 30 seconds in, it's 0.01. What is happening to my rate as the reaction goes forward? Decreasing, right? There is less A as time goes on because I'm making more B. So the rate decreases as the reaction goes forward. Right, it has to slow down. There's less stuff to use, and so the reaction rate is going to slow down. So if I know this information about B, I can then learn some things about A. So the question is, how is the rate of change of concentration A related to the rate of change? So this is what we did on Wednesday. I want to write an equation that looks something like, I guess I'll write it up here because I have lots of space. Rate equals so if I am looking at B, what fraction does B get? It gets 1/2. What fraction does A get? -1, right? Because it's disappearing. It's just -1 times delta A over delta T. Good. Now I have an equation that relates concentration change of A compared to concentration change of B. Right? So we're good there. Alright, so now I want to know, I know all the stuff about B, but now I have an equation that relates B to A. So now I can learn some things about A. So, first, find the rate of change for concentration A, looking at time 10 to 20 seconds. So which one of these data points, number 1, 2, 3, or 4, refers to the appropriate time gap? 2, right? 2, this one right here, is looking at this change in time. I never leave myself enough space between these questions. Let's just sit here. Alright, so the answer to this one's going to be here. Alright, so I have delta B over delta T is 0.0246 molarity per second. How do I find what this delta A over delta T is? You would think that. This is usually where we run. So I always want to do rate equals 1/2. Plug in the thing we have. Right, because if we think about it, this is right here, which means I just need to plug in this value for the green square. Since I already know it, I just need to plug it in for what this is. We're going to do a bunch more examples. It'll become more obvious. So it's just half of the B rate. No, rates are always positive. Rates always have to be positive. The only reason I have a negative sign in there is because if I looked at A final minus initial, it would be less. The concentration would be negative. And so I'm using the -1 to undo that negative sign. Let me just go ahead and write that up here. It's so important. Think about it this way. Let's say you were driving your car in the parking lot at 20 miles per hour. You then stop, put your car into reverse. Are you now going -20 miles per hour because you're going the opposite direction? No. Your rate is always positive. The direction that you're traveling may change, but your rate always has to be the same. Your speed would be positive, direction is negative. So that's what this is saying. That this is the direction, that in order for me to make it a positive number, I have to multiply it by -1. So I can compare them. Well, we're going to get to that one. We're not ready yet. Yeah. We're going to do some steps. That's my next example. Yeah. Correct. Yep. So really the negative sign is just telling me which direction the slope is going. Alright, so let's see. This rate is now, what is that, divided by 2? I think I can do this in my head. 0.0123. I think I picked it on purpose so I can do it in my head. Plus, that's a great number, right? 0.0123. All the numbers. Alright, so the last thing we're going to look at is what is the instantaneous rate at a given concentration. So I want to know about B when B is exactly this. If you don't have multicolored pens, I would recommend for this chapter. It may be easier later when you're looking at it. Alright, so I want to know about B at this concentration. Can I figure it out exactly at this concentration? Is there any way for me to plug it into this equation using just one dot, one concentration? Not really, right? I have to look, and I have to have a change, right? This is change in B over change in time. So which two times should I look at to tell me about this concentration? Well, 20 is right, and 40. So I'm going to look at 2 points around it. So I'm going to look to either side of it, and that'll tell me a pretty good instantaneous rate. So if I do that, alright, so it's going to be this B and that B. Which direction do I subtract? 0.89 minus 0.572 or 0.572 minus 0.89? Which one's the final? Yep. And then how big of a time gap am I looking at now? 20 seconds. No space for my units. Molarity per second. Good so far? We'll do a lot more of these, and they'll come a little bit easier. All right. Yes, those are average rates. Alright, let's do one without a data table, and maybe this will be a little more clear. Alright, so the question is, I have this equation. Nitrogen and hydrogen make ammonia. I want to know what are the relative rates. So I want to write an equation that looks like this, right? Rate equals fraction change equals fraction change equals fraction change. Alright, let's do the product first. I think it's easier to think about that way. Ammonia is a product, so what should its fraction be? Okay, what sign? Positive or negative? Okay, so it's a +1 half. Alright, looking at the ammonia, what should its fraction with its sign be? Yep, -1. And then what should my hydrogen fraction be? Yep, -1 half. Or 1/3, sorry, -1/3. Alright, I did this experiment and I determined this bit of information. I want to find out what the other two relative rates are, given that I know this part. So let's do this one. We'll do this one first. I want to find this part of the rate equation, or relative rate law. If I know this rate, right, this delta H over delta T, I'm going to plug it in right here. If I have this negative sign, what happens to this negative sign for the fraction? They kind of cancel out. So you can either write them both down and cancel them out, or you can just plug it in, however you want to think about it. I just take a third of that, 1.5 times 10 to the negative fourth polarity per minute. Alright, so then how do I find what the ammonia change is? So what you're going to do is you're going to, this is the trickier one, sort of, right? So now, I guess you have two options. You could either plug this one in, or you could use the one you just found. Either way would be okay. If you did it, nope, because this is a rate and it must be positive. Because I was looking for this. I was looking for the negative. I was saying this negative cancels that negative. Right, because I had negative 1/3, but I already had a negative sign in this part. So I'm using, for number 2, I'm comparing this to that. Alright, so 1/2 of the thing I want equals 1/3 of the thing I know. The same thing about the negative signs, they're going to cancel out. Now this is a positive value, so you're going to take 1/3 of it, and then what? How do I get this by itself? Multiply by 2. Which means for these rates to be equal, right, this one has to be half as fast, that one has to be 1/3 as fast. And so now I have the numbers to prove this. That one has to be slowed down by 1/3 compared to this one, has to be multiplied by 2 to be equal to that one. Excellent, you all look perplexed. Great, that's pretty much the point of the chapter. It'd be super confusing. So, as a reminder, 109 is going to require a lot more outside class time. And a lot more practice problems just because the concepts are kind of weird, right? Thinking about things in terms of negatives and where to plug things in, and the math is a little more complicated, even though this is just multiplying. Trying to figure out what you plug into what to multiply. So, Excellent, excellent, all right. Yeah, encouraging. Hopefully that excites you about, man, I can't wait to take the rest of this class. That's my inspirational note. Alright, so everything we just did was looking at overall reactions, right? We looked at a few points in time. We had average rates, instantaneous rates. In reality, like we saw in my little table over here, right? My reaction was really fast, and then it slowed down as I used up my reactant. If I want to figure out the maximum speed of my reaction, do I look at the beginning of the reaction or the end of the reaction? If I want to find out the maximum this reaction can go, I want to look at the beginning. If I look at the beginning, right, this is the fastest rate. So if I want to know the maximum speed, I got to look at the beginning of the reaction, which is called the initial rate. Alright, so I want to know the maximum speed, so I have to look at the very beginning of the reaction. I have tons and tons and tons of reactants, lots and lots and lots of stuff that can go on. So if I look at the initial rates, it'll tell me that information. And if I want to mess around with the concentration of the reactant, it'll be more obvious what the result's going to be if I do it at the beginning. If I do it towards the end, it's less obvious because there's some other things going on. If I want to see what I can do to make the reaction even faster, I have to do it at the beginning. Alright, so let's look at problems. We can draw a graph. Good. Alright, so let's say I have two dinitrogen pentoxides, and they're going to make 4 nitrogen dioxides and 1 oxygen. I went ahead and I looked at a bunch of different concentrations of reactants, right? And I saw how the rate changed. Right, so I had 0.1, it went this fast, at 0.2, it went this fast, 0.4, it went this fast, right? So I just changed it and see how fast the reaction went. Alright, so let's look at 2 points. 0.01 versus 0.02. What happened to the rate? Well, first of all, what happened to the concentration? Doubled. I doubled the concentration. What happened to the rate? Doubled also. Alright. 0.2 to 0.4. What happened to the concentration? Doubled. What happened to my rate? It doubled. Double the concentration, double the rate. What if I went from, what's the relationship between them? 0.01 and 0.1. What if I did multiply by? 10. Multiply by 10, what happens to my rate? Also multiply by 10. So there seems to be a direct relationship between the two. So much so that I could even throw out a graph. I didn't leave myself no space. Right, the rate was this. It should be nice and linear and look something like that, right? So as this doubles, that doubles, this doubles, that doubles, this doubles, that doubles. Right? Nice, straight, upward trending line. nothing crazy, just a linear slope. Slope. Right, slope's going to be a constant. Right, it's not exponential, it's nothing crazy, right? Straight up and down. Alright, let's figure out what that constant is. Rate and the concentration are directly equal using this proportionality constant K. The little k. We'll do big K's later. Little k. So wherever you write your little k, make it obvious that's little k. It will be in generally true. In generalities. I don't like to say anything's ever exactly true because you're going to take one more class after this and you're like, wait a minute. She told me, yeah, so because I was really simplifying things in this class. You're going to take other classes and you'll find out that this is the exception, really, not actually ever this nice. So. Alright, so slope happens to be this k. They're the same k's. This k is called our rate constant. So I now have a rate constant, which means I can then now calculate a rate constant. I now have an equation, right, and I know everything I can plug into it. So what if, let's do it like that. Let's say I'm looking at this final data point right here. I have the rate, and I have the concentration. I want to plug it into this equation and find K. So I plug in the rate. How do I get K by itself? Alright, divide by 0.1. Try to have the right units on this. Okay, if this is molarity and this is molarity per second, what is K's units then? Inverse seconds or per second? Both be fine. What if I picked a different set of data? What if I picked the 0.02 and the 0.036? What would the K be? The same, right? It's going to be the same for any one of these combinations. It is a constant for a given reaction. It's not a constant for... Yes. Okay, yes, no. It is a constant for a given reaction. It's not a constant for every reaction. So a given reaction has a rate constant. Which means we now have a general rule we can expand to look at all reactions. So here's my general form of the rate law. So let's say I have AAs and BBs make CCs and DDs. This, you can see, is different, right? If I was looking at the other rate, if I was looking at average rates, it would be right? That was the one we had earlier. This is now a rate law, which uses this K, this proportion, this rate constant. So they tell me very similar information. Just this, the per time is included in the K. Right, the K is in units of per second, which is what these fractions are. So they tell me similar information, it's just written a slightly different way. What is the one thing that's really different about the second equation? We have these exponents. Are the exponents anywhere in my general equation? No. They're called reaction orders. The exponents are reaction orders. And they have to be determined experimentally. So, looking at this first one, this average rate, do I have to do an experiment to figure out what these fractions are? No, right? They come right from the equation. But in order to determine these exponents, I actually have to do the experiment and see and collect data that looks like this, that tells me concentration and rate and how they're related. So that's two different ways of approaching a similar problem. This is experimental. This is just theoretical. I'm glad you asked. So if X and Y have to be determined experimentally, how do we do that? How do we go about finding them? And what do they tell us about the reaction? It's best if we do this as a graph. Obviously. Pretty much the answer to everything for 109 is, let's graph it. Let's see what it looks like. Because I'm a picture person. I'm more of a picture person than I am a words person. So I think sometimes a picture's easier. Alright, so our initial rates, looking at the experimental information at the beginning. So just like my little data table over here, right, I had different concentrations of my reactants, and I looked to see how the rate turned out. You measure several different starting amounts and see how that changes the rate. That's the initial rate law. So let's say I have something like this, where I look at rate versus concentration of reactant. I don't know what it is. Doesn't really matter. I'll say here's my reaction. Let's make it straightforward. Argus. Let's see. We'll make we'll make a table to go along with our graph. That seems sufficient. Alright, so the third column in my table we haven't talked about yet. We'll talk next time. Alright, so let's say, just like we had, keep coming back to my data table. Alright, so we had this concentration going to this concentration, right? We said the concentration doubled and the rate doubled. So let's do that as our first one. If I double the concentration of reactant, I double the rate. Alright, that was a nice straight line. This could be confusing. I just make this a star. It means multiplied by 2, not x. I'm going to use x over here. So if I double the rate of if I double the reaction concentration, the rate doubles. It's a nice straight, right, linear line, which means my exponent in my rate equation must be 1. Right, because just like we saw, when we double the concentration, you double the rate, and the K was just a constant all the time. So the exponent for that one is 1. So it's the order is called first order. That part shouldn't be confusing. These next 3 parts may be a little confusing. Alright. Well, if I double the R and the rate quadruple. Let's say I had concentration R is 0.3 and then 6. Rate went from so I doubled my rate, or I doubled my concentration, my rate quadrupled. If it was directly proportional, straight line, this is now going to be kind of a curved line, an exponential curve. And it's exponential, it now oh, sorry, I was using R's. R squared, right? Because I doubled this and this quadrupled, which means really if I square this concentration, then we're back to a linear line. Exactly. Yeah. Because all you can do experimentally is change concentration and then figure out how the rate changed. So if you double it and you double it, well, that's a relationship of 1. If I double it and that quadruples, well, then it's a squared relationship. That's second order. We're going to do one other one. It's going to seem like a trick. Ready? What if I have a straight line all the time? Regardless of what I did to the concentration, the rate stayed the same. What should the exponent be then? It's 0. Because what's something raised to the 0 power? Itself, which means rate equals K for this one. We call that 0 order. So these are going to be the 3 types of reactions you're going to see in our next bunch of work. Right, so either concentration doubles and the rate doubles, concentration doubles, rate quadruples, or concentration has no effect on the rate. Those are going to be the 3 we're going to look at. First order, second order, 0 order. Alright, I will stop there to make sure you have enough time for your quiz. And then when we come back on Monday, we will do a bunch of examples to try and get the hang of it. We're going to use some natural logs, base 10 logs. Very, very exciting stuff coming up.